This is our ELL project and we'll be showing the implementation of binary operations. So let's start at the very beginning, that is, the beginning of computation.
Computers have evolved from calculators. As maths and science progressed, we needed machines that could perform operations on large numbers quickly and accurately.
The first mechanical computer built was the Pascaline, invented by Blaise Pascal. It could perform some elementary calculations.
The ENIAC was the first electronic computer used for numeric computation. It could perform up to 350 calculations per second.
While computers like ENIAC were several meters long, modern computers can even fit into your pocket.
These are some of the systems that were made during the evolutionary period.
Now we come to the modern computers. Well, the use of modern computers need not be obviously explained.
All of this has been possible due to the invention of integrated circuits, composed of large number of diodes and transistors which can fit in a very small chip.
Here's a fun fact. If a processor were a country and transistors its population, a modern processor would be the third most populated country, just behind India and China, with over a billion members.
To estimate the speed of modern computers, let's have a thought experiment. Consider a lamp kept on a table. In the time light can travels from the lamp to the table, where we consider the distance to be approximately a foot, the CPU can perform two calculations.
To get an even better feel of it, take this example. If we take a kid's ball and let it fall from a height of roughly 1 meter, then the time in which the ball touches the ground, your computer would have performed 1 billion calculations. Now that's fast.
But the basic question is, how do computers add at the circuit level?
We know that computers store data in binary, hence numbers are also stored and processed in binary.
Addition. It is performed by the binary adder circuit. It is of two types, half adder and full adder.
The half adder circuit adds 2 bits and returns the sum and the carryover. The sum is given by A's or B and the carryover is A and B.
The binary full adder takes three inputs. That includes a carryover from the previous addition.
So this is the truth table and the logical expression for the two outputs.
This diagram shows the various inputs for varying outputs for a full adder, such as when the two inputs are 1 and carry in equal to 0, then the sum bit is 0 and carry out is 1.
So the multiple full adders can be attached to make an n-bit full adder. Now we come to binary subtractors.
The half subtractor consists of two inputs and the output consists of the difference and the borrow over which will be passed to the next subtraction.
Another possible method for computing the subtraction is by the 2's complement method. For example, if we're computing 5 minus 3, what we can do is we can take the 2's complement of 3, which is obtained by inverting each bit individually and then adding 1. Now adding 5 in the 2's complement of 3 would give us the final result, which is 2.
The shift and okay. Now we come to binary multiplication. While the electronic circuit may seem complex, it is based on a simple idea that we learned in primary school.
The shift and add algorithm involves multiplying one of the numbers by each bit of the second number and shifting and adding at each step. This is same as the one that we did in decimal numbers, but here the number system is binary. Thank you.